The universe is a vast and wondrous place, filled with countless stars and galaxies. But have you ever wondered about the building blocks of these celestial bodies? The elements that make up everything we see, from the air we breathe to the ground beneath our feet.
Where do the elements that make up our world come from? The answer is simple. While the Big Bang created hydrogen and helium, heavier elements are forged in the endless environments of stars. This video explores stellar nucleosynthesis, supernova, and neutron star mergers, the cosmic processes responsible for creating the building blocks of planets, stars, and life itself.
This rock, this planet, even you are made of stardust. We're going to uncover the incredible story of how the universe cooks up heavy elements. From the gentle simmer of a star's core to the explosive supernovae that scatter their creations across the cosmos.
The world we live today is just a small part of our universe. This video will focus on one of those wonderful things present in outer space, the stars. Although our stars are millions of light years away from us, we can still see them twinkling in the sky. Let's find out how they emit light and what keeps them shining for a long time. Stellar nucleosynthesis is the process by which stars create new chemical elements through nuclear fusion reaction with these cores. Stellar nucleosynthesis is a fundamental process, astrophysics explaining chemical composition of the universe and the origin of elements that make up everything we know.
So the first is the history of the universe based on the Big Bang Theory. The Big Bang Theory describes the evolution of the universe from an extremely hot, dense state approximately 13.8 billion years ago to its present state. Here's a timeline based on the theory.
To begin with, Planck's epoch, 0 to 10 raised to negative 43 seconds. This is the earliest period where the universe was incredibly hot and dense, smaller than a single atom. Our current physics breaks down and cannot describe this era.
The second stage is grand unification epoch, 10 raised to negative 43 to 10 raised to negative 36. Gravity separates from the other fundamental forces, electromagnetism, strong and weak nuclear forces. Inflationary epoch, 10 raised to negative 36 to 10 raised to negative 32 seconds. The universe undergoes a period of extremely rapid expansion, smoothing out irregularities and explaining the observed uniformity of the cosmos. Electric epoch, 10 raised to negative 32 to 10 raised to negative 12 seconds. The electromagnetic and weak nuclear forces are ununified. Elementary particles begin to form.
Quark epoch, 10 raised to negative 12 to 10 raised to negative 6 seconds. Quarks and gluons exist freely.
Hadron epoch 10 raised to negative 6 to 1 second. Quarks combine to form protons and neutrons called hadrons.
Lepton epoch, 1 second to 10 seconds. Leptons, electrons, muons, and etc. are dominant. Neutrons decouple from other particles.
Nucleosynthesis, 10 seconds to 20 minutes. Protons and neutrons fuse to form light atomic nuclei, primarily hydrogen and helium, along with small amounts of deuterium, lithium, and beryllium. This is Big Bang nucleosynthesis.
Photon epoch, 20 minutes to 380,000 years. The universe is dominated by photons light. The temperature is too high for atoms to form. Electrons are filled and interact strongly with photons.
Recombination of 380,000 years. The universe cools enough for protons and electrons to combine and form neutral hydrogen atoms. Photons decouple and can travel freely, forming the cosmic microwave background radiation or CMB.
Dark Ages, the 80,000 years to 150 million years. The universe is dark and relatively featureless. Gravity slowly begins to pull matter together. Rheaization, 150 million to 1 billion years, the first stars and galaxies formed, emitting ultraviolet radiation that ionizes the neutral hydrogen. Structure formation, 1 billion years to present. Gravity continues to form matter together, forming stars, galaxies, clusters, and superclusters. The universe continues to expand. Present day, 13.8 billion years. The universe continues to expand, with galaxies moving away from each other. Stars are born and die, creating heavier elements through stellar nucleosynthesis. Right after Big Bang, protons and neutrons combine together and form light elements, hydrogen and helium in the process of Big Bang nucleosynthesis. Other light elements such as lithium and beryllium were also formed during this process.
The early universe. Immediately after the Big Bang, the universe was incredibly hot and dense. The temperature was so high that the fundamental particles, quarks, and leptons existed as a plasma. As the universe expanded and cooled, these particles began to interact and combine.
Proton and neutron formation. As the temperature dropped below a critical point, quarks combine to form protons and neutrons. These are the building blocks of atomic nuclei. The ratio of protons to neutrons at this stage was roughly 1:1, but it shifted slightly in favor of protons as the universe continued to cool.
Big Bang nucleosynthesis, or BBN. Once the temperature dropped further, protons and neutrons began to fuse together through a process of nuclear reactions, forming the light elements.
Big Bang nucleosynthesis resulted in a universe with a specific abundance of light elements. Approximately 75% of the ordinary matter, such as baryonic matter, in the universe was hydrogen and about 25% was helium. The other light elements such as deuterium, lithium, beryllium were present in much smaller quantities. These abundances are consistent with observation and serve as a strong evidence for Big Bang theory. Soil life cycle diagram. As we can see, diagram depicts the life cycle of both average sun-like and massive stars. Average star. An average star is a star like our sun.
Massive star. Massive star is much bigger than an average star. It burns its fuel very quickly and has a shorter proton chain reaction or PP chain. What is it? The PP chain is the main way our sun and smaller stars produce energy by converting hydrogen into helium. How is it formed? It happens naturally in stars like the sun because of the extreme heat, millions of degrees and pressure in their core. Carbon, nitrogen, oxygen cycle or CNO. What is it? The CNO cycle is another way stars produce energy, mainly in big stars. It uses carbon, nitrogen, and oxygen as catalysts to fuse hydrogen into helium.
Triple alpha process. What is it? The triple alpha process creates helium and carbon when stars run out of hydrogen to fuse.
Neutron capture. What is it? Neutron capture is a process where an atom captures free neutrons, creating heavy elements.
Neutron capture can be slow or rapid. The S process creates heavy elements slowly by adding neutrons one at a time to a nucleus. How is it formed? This happens in old stars during their stable lives when there is enough time for nuclei to capture neutrons slowly. R process, rapid neutron capture. What is it? The R process happens quickly and creates very heavy elements like gold and uranium.